In this video, we're going to take a look at the idea of graphing cones. In our first example, we're going to try to graph the surface z equal root x squared plus y squared using contour curves. So let's think back to our previous videos and let's just refresh our memories on what contour curves are. So we could say that a contour curve is the curve that's produced when we take any surface and we intersect it with the horizontal plane z equals c, where c is some constant. So let's try plugging in some z values here. We could do, say, z equals 0, plug that into the equation for our surface. We'll see what happens. Similarly, we could try, say, z equal 1, maybe z equal 2, and maybe a negative value like z equal -1. So that's going to give us some information about what our surface looks like. Right, so let's try this for z equals 0. Plugging in to the equation that we've got up here, the equation for our surface, we'd have 0 equals root x squared plus y squared. That might look more familiar if we square both sides and we just write x squared plus y squared equals 0. In other words, that's a circle of radius 0. Or if we say that more simply, if we were talking about a curve in the xy plane, that would just look like the origin in the xy plane, just the point 0, 0. All right, so for some other z values here, if we plug in z equal 1, we'd have 1 equals root x squared plus y squared. Same kind of idea, let's square both sides. We'd have x squared plus y squared equals 1. And what that looks like in the xy plane, that's a circle of radius 1. So let's try one more positive z value. If we do z equal 2, sub that into the equation for our surface, we'd have 2 equals the square root of x squared plus y squared. That might look more familiar if we were to square both sides. We could say x squared plus y squared equals 4, and that gives us a circle of radius 2. So from there, we can probably deduce the pattern that if we let z equal any positive value, say call that value c, what we'd be producing is a circle of radius c. All right, so let's try a negative z value. If we were to plug in something like z equal -1, we'd have -1 equals square root of x squared plus y squared. And that equation there has no real solution. We're only interested in real number solutions in multivariable calculus. So no solution there. That tells us that there are not going to be any points on the surface corresponding to z equal -1. So let's see how we can use these contour curves to graph our surface. So let's see if we can draw our surface in 3D using these contour curves. So here are our three axes, our x, y, and z axes. So let's think first about the contour curve for z equals 0. So that is sitting at a height of z equals 0. And what that's producing in the x and y directions is a circle of radius 0. So in other words, we're just getting a point, just that single point there, the point 0, 0, 0. All right, now things will get more interesting as we look at various heights above the xy plane. So let's look up in the z direction here. So we'll just indicate some scale in the z direction. Let's say this is 1 and 2 units above the xy plane. And we might want some scale in the x and y directions as well, just for what we're about to draw. Okay, so let's see. Let's say each tick here represents 1 unit in each direction. So at the height of z equal 1, the cross section of our surface looks like a circle of radius 1. So that's what we said back over here. So at that appropriate z level z equal 1, we're getting a circle of radius 1. So maybe we draw that something like that. And as we take various horizontal cross sections here, we're cutting through the surface at various constant z levels. So say at z equal 2, what are we getting? We said we're getting a circle of radius 2. So let's draw that in our picture. Z equal 2, circle of radius 2. So you can imagine what's going to happen here as we look at various z levels. We're going to be producing circles of a corresponding radius. We already said above, if you cut through at z equals c, you would expect a circle of radius c. So if you were to draw all the cross sections above the xy plane here, we'd be producing a surface that looks like this. It's just giving us a nice cone. And we also said that if we look at any z values that are negative, we're not expecting to see any points down here. So sure enough, this cone is opening upwards. We're only seeing points on the cone on or above the xy plane. And we could draw a cleaner picture just over to the side to illustrate that. So there's our cone. It's an infinite surface, but we tend to draw it finite just to show the perspective. So you could draw dotted lines going up in those directions if you wanted. And it is hollow, so I like to just imagine the cone as being formed from an infinitely thin piece of fabric. We're just talking about this outer surface of the cone. So now that we've seen how to draw our basic cone, let's talk briefly about some transformations. So we're going to look at three different surfaces here. One has equation z equal root x squared plus y squared. So that's the familiar cone that we drew above. And we're going to talk about a couple of transformations of this. So we'll look at z equal negative root x squared plus y squared. And we'll also talk about z squared equals x squared plus y squared. And we'll figure out what these bottom two surfaces look like just by applying a transformation to our top surface. So just to recall what we said above, we said if you see the equation z equal root x squared plus y squared, automatically now you want to think to yourself, oh, yep, that's a cone with vertex at the origin and it's opening upwards. So there's our classic cone. Now, if we were instead to talk about z equal negative root x squared plus y squared, we would be talking about a reflection in the z direction. So instead of this cone opening upwards, it's now opening downwards. So here's what our cone would look like. Still got its vertex at the origin, but now opening downwards. And you can draw a dotted line there just to show some perspective on the back of the cone. Okay, now last transformation we could look at here. If we had, say, z squared equal x squared plus y squared, you could think about this equation in a slightly different way. You could say, well, we could take square roots of both sides, but if we did that, there would really be two corresponding solutions here. Z would be either plus or minus the square root of x squared plus y squared. So if you think about this, if you take this bottom equation here that has the plus or minus in it, and you square both sides, sure enough, either way you would get z squared equal x squared plus y squared. So what that tells us is that when we draw this cone, we've really got two different surfaces that are being patched together. We've got the cone that's opening upwards, and at the same time, we've also got the cone that is opening downwards. And so when we talk about this cone, if we want to emphasize the fact that it's opening both upwards and downwards, we sometimes call this a cone with two naps. So nap is just the fancy name for the half of the cone that's opening either upwards or downwards. So in both of these top two situations, we would just say that's a cone. Or if you want to be fancy, you could say it's a cone with one nap. So now we've had a bit more practice with graphing cones. Thanks for watching.